Okay, yes, I am James McGugan, and this summer I've been researching the selective population and decay of neutron unbound states in the exotic nucleus beryllium-13. So this is a chart of the nuclides. Probably some of you are familiar with this. The stable isotopes, of which there are fewer than 300, are depicted in black here in the center. These have roughly even numbers of protons and neutrons. As we add or subtract neutrons, the nuclei become unstable and decay. Half-lives are depicted here on this color scale here. As we move further away from the so-called valley of stability, the half-lives of the nuclei falls off rapidly. Say, for instance, that we are adding neutrons to the nucleus. At a certain point, the nucleus will become fully saturated with neutrons. It just can't take any more. We can put another neutron on, it'll just fall right off. We say that for this, the binding energy of the outermost valence neutron is literally less than or equal to 0. So this is called a neutron unbound nucleus. And separating the neutron unbound nuclei from the neutron bound nuclei is what's called the neutron drip line, which is shown here. It's this black line, black jagged line going up the chart. And so the nucleus that I have been researching should be right here, beryllium-13. So beryllium-13 is just beyond the neutron drip line, and in fact surrounded on 3 sides by bound nuclei. Though you wouldn't know it from the decay time of beryllium-13. This is a picture of the half-lives of beryllium-13 and its nearest neighbors. Beryllium-12 and beryllium-14 decay in centiseconds and milliseconds. Yet beryllium-13 only survives for zeptoseconds. That's 10 to the negative 21st seconds. So just adding 1 neutron makes the nucleus survive an astonishing 18 orders of magnitude longer. So beryllium-13 is an excellent place to study the neutron drip line because it lies right along the line and highlights the astonishing contrast between neutron-bound and neutron-unbound nuclei. Another reason it's interesting is it's just 1 neutron away from a closed shell at beryllium-12, which has 8 neutrons. Neutrons and protons form shells in the nucleus the same way that electrons form shells in the atom. And 8 neutrons is a closed shell. So beryllium-13 is decaying into a closed shell. So we want to understand this decay process. And we do that by finding the decay energy of beryllium-13. The decay energy, given here, we're just using E equals mc squared in natural units. So c squared is equal to 1 and left out. We know the masses of the decay particles. So all we need to find is the mass of beryllium-13. That is given by this equation here. Again, we know the masses of the decay particles, beryllium-12, and the neutron it decays into. We need to find the energies of the decay particles, the momenta of the decay particles, and the angle at which the decay particles split apart. So for that, we need position detectors, timing detectors to find the velocity, and scintillators. Once we know the decay energy, that's going to tell us information about the energy states of beryllium-13, and in turn information about the discrete energy levels of the outermost valence neutrons. Those we can then compare to existing shell model calculations. So work on this research was actually recently completed by a team working in Japan, and their experiment awaits confirmation. But we have their results, and the Japanese saw something interesting. These are 2 competing shell model calculations for the energy levels of valence neutrons in beryllium-13. They do not agree. Which is correct? Well, it would seem neither. This is what the Japanese actually saw. So this is really what we're driving at with this experiment. And the experiment itself was performed at Michigan State University at the National Superconducting Cyclotron Laboratory. This is a facility that specializes in producing beams of rare isotopes. So this is a schematic of the detector system in our experiment vault. our beam consisted of beryllium-14 particles traveling an appreciable fraction of the speed of light, about 50% of c. These nuclei entered our experiment vault. First thing they did was pass through these two position detectors here and here, and then they encounter the reaction target. They slam into the reaction target and pass through it. Violent reaction occurs in the reaction target when the target is made of deuterated polyethylene. That converts the beryllium-14 into a cocktail of new nuclei, including beryllium-13. Since beryllium-13 only survives for zeptoseconds, even at relativistic speeds, it's not going to travel more than about picometers. So it decays immediately into beryllium-12 and a neutron. These are our decay particles, the things we actually need to measure to find the decay energy of beryllium-13. Those immediately encounter the sweeper magnet here, which actually sweeps the charged beryllium-12 core towards these detectors down here. The neutron, meanwhile, could not care less that it's in a magnetic field and just keeps going straight ahead, and is captured by MONA, the modular neutron array, which is our neutron detector. Meanwhile, the beryllium-12 nucleus proceeds through these position detectors here and here, passes through the ion chamber, which we actually did not use in this experiment, and lands in a pair of scintillators at the bottom here. We have a thin scintillator, which measures the change in energy as the particles pass through, and is also a timing detector. And then there is a thick scintillator, which is thick enough to actually capture the particles and measure their total energies. So this is a huge experiment. It's a collaboration of about 10 schools plus Michigan State. And the analysis process takes about 2 years. We just began this summer. So far, what we've been doing so far has been calibrating the numerous detectors in the detector system. Like, for instance, each of these detectors has 128 pads within it that all need to be individually looked at. So I'll just show you as the last thing I do here, a couple of the procedures that I've been doing. I'll show you what I've done with the thin and thick scintillators here. This is a schematic of the two scintillators. They work on much the same principle. One is just thicker than the other. They consist of translucent blocks of scintillating material surrounded by 4 photomultiplier tubes. So the particles pass through the scintillating blocks, emit a flash of light, and that light is detected by the photomultiplier tubes, or PMTs, and converted to an electrical impulse. So now, in an ideal world, all the 4 PMTs would deliver the same output given the same input. Of course, in reality, this doesn't actually happen. The electronic gains of the 4 PMTs are in fact not matched up. It's impossible to do so, so we have to do that using software. So the way we do that is we run a centered beam through the detectors. This is a plot of position in millimeters versus y position in millimeters, x and y, and that is the beam. And then we gate that data set on just the center of the detector, equidistant from the 4 photomultiplier tubes. That's ensuring that the 4 tubes are receiving the same input. So they should all deliver the same output. And of course, they do not. These are plots of the charge measured by the 4 tubes. These Gaussians should all be lined up over the same values, and they're not, so we have to make them that way. So I went through and I found the centroids of all these peaks, and to make a long story short, I plugged them into our computer code and had the computer apply a multiplying factor and an offset to line up the 4 peaks, like so. Another thing that I did was position correct. These are not position detectors yet. They directly measure light intensity, which varies with distance squared. So depending on the trajectory of the particle through the scintillator, we're going to get different outputs, which is not what we want. So we have to fix that. So we do what's called a sweep run, where we have the sweeper magnet literally sweep the beam from one side of the detector to the other. And this is a plot of what we get. Position, again, in the x-axis, millimeters versus charge. This should be a flat bar. That's what we want, showing that it's giving us the same output at all positions. So to make that happen, I plotted the data points with error bars along the line of maximum activity and did a polynomial fit to that data. This is a first-order fit for the thick scintillator and a fourth order fit for the thin scintillator. And I plug the parameters of those fits into our computer code and have the computer line up the output, like so. Again, that's before, and after. So I guess I'm out of time. So I would like to thank Ohio Wesleyan for hosting me this summer, and all the people here who put up with me, and the National Science Foundation for helping fund this research, and especially for funding my research this summer, and lastly, the NSCL at Michigan State University. And of course, thank you.
Okay, thank you, James. This paper is now open for discussion. Questions?
Yes.
Is there a reason why you choose to fit a polynomial function instead of some other? I notice there's lack of fit in the right tail. And I wonder if there's some physical reason why you would choose to fit a polynomial there instead of some other function.
I can choose whatever. Well, I can choose whatever order I like. To actually improve this fit, I had to go up to like 8th or 9th order to actually get something closer than this. And at the degree of precision that we're dealing with, it just wasn't worth going that far.
But is there a physical justification for a polynomial model? Is there some other model that might obey physical constraints or physical interpretation of the problem? So it's not simply a data fitting exercise, but some sort of a physical.
I do not know the mathematical reason behind that.
There's no physics behind the fit, actually. It's just the artifact of detector response.
Okay.
So really, it's just the fitting to the points.
Okay.
Yeah.
Yes.
Maybe you said it and I missed it, but is there any kind of relatively simple explanation of why it should be that if I try to add one neutron to beryllium-12, it decays in zeptoseconds, whereas if I add two, all of a sudden it's much longer decay?
Right. It's very counterintuitive. One would think that we add a neutron and a neutron and a neutron, all of a sudden the nucleus is unbound. We go, aha, we found the drip line, now everything after this will be unbound. But then we add another neutron and suddenly it's bound again. Very strange. This is due to what's called light nucleon pairing. The neutrons and protons, for that matter, arrange themselves in shells in pairs, so that the sort of the nucleus is happiest when these spin when it has zero angular momentum. So the neutrons arrange themselves in a shell in spin up and spin down pairs, which cancel each other and deliver zero angular momentum. So when you have an odd number of neutrons, you have to have at least one neutron, which is either spin up or spin down. Angular momentum is not zero. And that sort of corrupts the stability of the nucleus, apparently a lot. So that's what causes that sort of shape all up the neutron drip line, where odd numbers of neutrons, nucleic odd numbers of neutrons are unbound, while even numbered ones remain bound.
So essentially, if you're adding two neutrons, they interact with one another, and that lowers the overall energy, and that makes them happy? Is that the...
Simply put, the strong nuclear force favors light nucleon pairing. So you can almost think of it as the well is deeper, so to speak. I mean, it really is a strong effect of the nuclear force. Simply having an even number of protons and or neutrons has a big effect.
Yes.
When in beryllium, you have this giant leap or gap in lifetimes, like a huge jump stability. But if you look at all the nucleons, would you see a gap if you look at all the lifetimes, collect them all? Is there like, I guess, a global notion of instability in that sense? Like, or
You mean for other numbers of protons or for other numbers of neutrons?
all of them. So within beryllium, you have a big gap in lifetimes. If you plotted all, or tabulated all the lifetimes of all the nucleons we've ever experimented with, would there be a big gap? Like all the stable ones are above this lifetime and all the unstable ones are below this time?
Or you mean unbound versus bound?
Yes.
Oh, yeah. Usually the unbound nuclei are have dramatically shorter lifespans by many orders of magnitude. Some unstable nuclei can still have pretty short lifetimes, though not anywhere close to sort of negative 10 to the negative 21st. There are some stable nuclei sort of 10 to the negative 8 second lifetimes around that, but that's a pretty significant jump. So yeah, in general, I think you would see a pretty significant drop in lifetime going from bound to unbound, pretty much everywhere.
But I think maybe because within the same elements, I would expect to see a significant drop. But I guess let me phrase it this way: the shortest lifetime of a bound nucleon versus the longest lifetime of an unbound nucleon. Is there a big gap as well of all the nucleons?
Yes.
Okay.
Yes.
And then I guess one more question: does the drip line? It seems like there's two components: one on the upper side of the graph and on the lower side. But is the drip line, is that it? Just this component, or does it ever do a circle? Just out of curiosity, wrap around.
Let me go back after that. You mean? So you mean? So there's one here and there's another one here.
There,
meet? You mean?
Huh?
Do they meet at the top?
Well, yeah. Could they meet, or do they ever encase a nucleon so that you have this nucleon in the middle of stability that's unstable?
I don't know what's happening up at the very top of the chunk, but I sort of
No.
Okay. All right. Thank you.
The reason for the wraparound beryllium is because he's at beryllium 14 has an even number of neutrons, so you get this pairing effect that he discussed earlier. Otherwise, there might be just one spot for a given isotope where the drip line resides. But there is another one on the other side, on the west side of the landscape, the proton drip line, but we're not looking there right now.
Oh, okay.
Okay, let's thank our speaker again.